The visual signature of Pareto distribution is a straight line in the log-log plot of the tail distribution, because we can easily see that the log of the tail distribution, log of the probability that a Paretoli distributed random variable is bigger than or greater than a fixed number x equals minus alpha log of x plus alpha times log of k. Now, since k is a constant, this is just an offset. What matters is that the log of this tail probability is minus alpha times the log of x. So on the log-log plot, it is a straight line with a negative slope of minus alpha. So this slope is minus alpha. And this is how usually we depict Pareto, or in general a long tail distribution, either the distribution itself or the tail distribution on the log-log plot, and see a straight line. And the slope of the straight line indicates the decay exponent. So this decay exponent has been observed to be something like minus 2.1 for the in degree of web page graphs, or minus 2.4 for the out degree of web page graphs, or minus 2.38 for router graphs. It has been discovered that many different networks exhibit the scale-free property, in the sense that their node degree have the following distribution or tail distribution that follows, say, Pareto or other long tail distributions. Okay, now let's just clarify before going any further that scale-free network in this lecture is not the small world networks in the previous lecture, number 9. Okay. In particular, scale-free property of a network concerns only with the distribution of the node degrees, and is entirely a topological property. We will see that its implications to functionality, such as robustness to attacks on certain routers, differs dependent on other factors. In contrast, small world is a property of a network concerning the existence and discoverability of short path between node pairs. And therefore it is both structural or topological, as we saw explained through Watt-Strogas, as well as functional, as we saw in algorithmic small world. Okay. Now, of course, a network could be both small world and scale-free. And indeed, in advanced material part of last lecture, we saw models that can make that happen. All right, now back to the scale-free network and the Achilles heel of the internet. In the late 90s to 2000, certain researchers discovered that, hey, the internet router graph also exhibit this straight line on log-log plot. It also has a Pareto distribution of the node degree sequence. That means it is robust against random attacks. Okay, because if you randomly pick a router to attack, it's likely that it will not be destroying many connected paths. But it is susceptible to attack on the most highly connected nodes. These are the routers that has the largest degree, and because it's a scale-free network, there can be routers with a really big degree. And if they target attack exactly on those networks, then something bad will happen, because these nodes are sitting in the middle of the network, meaning it's in the middle of many paths. And therefore, if these nodes go down, they're going to break up the entire internet into many individual pieces. So this router is sitting in the middle with many degrees. It's among the most highly connected nodes in the network, and yet it is in the center of the network, and thereby destroying it will bring down the network by destroying it into many small pieces. And therefore this node is the Achilles heel of the internet. Now this is a a very alarming statement, and it almost sounded like true, except it is not true. Again, internet has many vulnerabilities in terms of security and reliability, but it doesn't have a highly connected router sitting in the middle of the network. What is internet's reality then? Here's a multiple choice with two choices. Graph A shows a typical Achilles heel kind of network. You've got very highly connected nodes like these two sitting in the center of the network. And graph B turns out to have the same degree distribution. If you just look at degree distribution, you cannot tell the difference between the two. But they clearly look very different. In other words, you can have two very different looking networks sharing the same no degree distribution, say Pareto distribution. Okay, distribution of no degree does not lead to a unique type of network topology. In particular, in this network topology, you see some of these edge nodes are very highly connected. Okay. And in fact, as you go into the core of the network, you get a much sparser connectivity pattern. A lot of these nodes are only medium to low degree. So if you attack the most highly connected degrees nodes, you're going to just bring down certain edge networks of the internet rather than destroying the entire network by breaking down the core of the network. Whereas if you want to target mediumly connected nodes, there are too many of them. Remember the degree distribution. If you target medium connected nodes, then there are a whole lot of them. It's not exactly easy to know where they are. Not necessarily we'll be attacking these particular nodes. In other words, highly connected nodes, routers with a lot of interfaces, are actually more likely, much more likely, sitting on the edge. And what's in the middle is usually medium to low degree. That is the internet's reality. This picture does not fit the empirical data, does not fit the actual AS, does not fit the actual router graph. So you may wonder, why not in the middle? And the clear answer is the following: because you cannot have both a large degree, many interfaces on the router, and a large bandwidth per degree, a high speed supported on each interface. Later in chapter 13, we'll look at a little bit of router architecture, and we'll see that there is a constraint of total processing bandwidth. How many packets per second this router can actually process. And this number, let's say 1,000 in some unit, you can view that as 10 degrees and 10 nodes that can be connected to this router, and then each of them can be sending, say, 100 certain units, say 100 mega packets per second to this router. Or it can be decomposed into 100 degree, and then each interface, however, can only support 10, say, megabits or mega packets per second. So there is an intrinsic trade-off between degree, how many can you talk to, and the bandwidth per degree. And the router sitting in the middle of the network, these kind of routers, by necessity, must have a large bandwidth per degree, because there are layers of aggregation of traffic and statistical multiplexing. Again, later in chapter 13, we'll talk more about this. But as you go from your home, your workplace, your campus, through many layers of aggregation, each time there's aggregation, you have more and more traffic. And by the time you get to the core of the network, these core routers, you must support a large bandwidth per degree. You have to process many packets for each interface, and therefore you cannot possibly have too many interfaces. This option is not going to scale the network. Instead, you will have fewer nodes connected to you, and then can support a high speed per interface. And that's because their product has to be constrained by technology and economic realities. Here's a typical chart showing some of the state-of-the-art in 2002 Cisco core routers, and some of the aggregators, and some of the edge switches. On the y-axis is the total bandwidth, okay, and the y is the router degree in log scale. You can see that there are some performance boundary that says the total bandwidth, okay, is already fixed. As you increase the node degree, you're going to suffer in the bandwidth per degree. And you cannot arbitrarily increase both this number and that number, because their product is capped for different kind of router families. In other words, Cisco and Juniper, the top two core router manufacturers in the world, they cannot possibly manufacture a router that can make their total bandwidth to be very big. In the end, you have to come down to be a trade-off. And for performance reason, you're going to have a large bandwidth per degree at the expense of smaller degree. Now, but still, you may say, I still have other questions. Okay, for example, what about long-tail distribution? Well, as we just saw that you can have two networks, A and B. Both are long-tail distribution in their node degree sequence, but they look very different and have very different properties other than their node degrees, which they share the same distribution. In other words, node degree distribution does not imply actual entire topology. This is a very crude summary of the topology. The second objection might be, but that's not likely. What is not likely? You may say that this kind of graph is not likely. This is more likely. And indeed, in the next module of the video for this lecture, we will indeed quantify the notion that this is much more likely and this is highly unlikely. In other words, if I have a bag, a set of many topologies, each ball in the bag or each point element in this set is a topology, and they all satisfy power law or this long-tail distribution such as Pareto for their node degrees. And I randomly draw one out of the bag. The chance that it will look like this with highly connected nodes in the middle is much higher than the probability of drawing something that looked like this. And indeed, the internet reality is much less likely. However, internet was not drawn at random. It was designed instead with economic objective. We're coming to that in the next lecture. And simply put, we say that we want to maximize the throughput going through the network, because that's how revenue will be generated, subject to technology constraint. For example, I cannot make an arbitrarily high bandwidth, total bandwidth router, and therefore I must face a trade-off between bandwidth per degree and the degree itself. So even though it is not as likely to be drawn at random, we just have to realize internet was never evolved as a random object. It was designed with constraints and objective functions. The third objection might be, what about preferential attachment? You might have heard about this phrase, and we have refrained from bringing this up to this point. We will bring them up in the next module of the video, and a lot more in the advanced material. But roughly speaking, it says that the rich gets richer phenomena. Okay? As you add more nodes, they will have a tendency to aggregate, to attach to those nodes with already a large degree. So a highly connected node gets even more highly connected. And this is what's called preferential attachment. It turns out that preferential attachment can A, generate this scale-free network, and B, it will lead to Achilles heels. The highly connected node sitting in the middle of the network, that phenomena will be true if preferential attachment is indeed the case. So you may wonder, gee, preferential attachment generates scale-free and leads to Achilles heel. So shouldn't scale-free network have Achilles heel? Not quite. That's actually a logically incorrect statement, because it's not the only generative model. There are also other generative models that can also generate what we observe in node degree distribution and yet do not lead to Achilles heel, such as what's called constraint optimization model. We'll go visit in the next module of the video. In other words, preferential attachment, PA in short, implies scale-free network and implies Achilles heel. That, however, does not mean that scale-free implies Achilles heel, because constraint optimization and other models can also generate scale-free network. So scale-free network does not imply either or any of these generative model. Generative model is a hindsight explanatory process. Okay, they both can generate our empirical observation. The existence of this observation does not logically imply either of them is correct, and therefore does not imply Achilles heel. In short, there are three fallacies in this Achilles heel issue. First, the measurement is actually incomplete, and that skews the data. We actually don't know if the node degree distribution is indeed Pareto. Second, even if it is, power law distribution does not imply preferential attachment and therefore does not imply Achilles heel necessarily. In fact, if you look at the internet reality, you see that in AT&T's 2003 networks, the highly connected nodes are on the edge. Okay, the maximum degree of the core router is only 68, but the degree of the edge router was 313, much bigger. And finally, as we briefly mentioned, there's also functional protection on top of the topological properties. So we focused on this part of the logical fallacies, but if you couple all three, that completes the discussion of why the internet actually does not have Achilles heel, and you can see why people might have thought that it could have Achilles heel. But both the empirical evidence from carriers and router vendors, as well as just logical discussion, show that the internet does not have this kind of vulnerability.